Good morning and welcome to a new session on Introduction to Photonics. So, the next couple of lectures we are going to sort of switch tracks to a new module, and before I do that I thought we should go back and review what we have seen so far. So, we started looking at the science of light as far as this course is concerned, from the perspective of ray optics, where we look at propagation of light in terms of straight lines that we call as rays. And then we said, okay, that is going to be limited in terms of its utility, because light may be treated as waves, in which case you have phase and a wavelength that can be used to describe light, and so we had been looking at wave optics, and we are at a point where we are sort of at a crossroads between wave optics and actually treating light as particles in terms of photons. I say that because, as you know, in the last few lectures we have been looking at the concept of coherence of light, and we defined what temporal coherence and spatial coherence means, and that is to say, in practical light sources there is a certain level of randomness associated with the propagation of light, a certain level of randomness associated with the generation of light itself. We will come back and look at that in the next few weeks, but as of now we are just characterizing light propagation, and we are saying that quantifying that randomness is what we are trying to do in terms of temporal coherence, where we say, okay, light may actually be polychromatic, may have multiple colors, and because of that you may not be able to get perfect correlation when you take one wavefront and interfere with another, a delayed wavefront, right. That is what we have been seeing with the Michelson interferometer, and of course we saw that we could define a coherence time and through that a coherence length, and of course some of you that are taking this course here have been able to do this experiment in the lab, where you are actually experiencing or figuring out how to quantify temporal coherence, okay. And you also looked at spatial coherence, which essentially says that, okay, your light wave is not going to be a plain electromagnetic wave all times, right. So, there is no such thing as a perfect plane wave in practical sources. So, you typically deal with a subtension of wave vectors, a subtension of angles as far as the source is concerned, and we are trying to quantify that through this spatial coherence length, which we have mentioned as rho c over here, and that spatial coherence length determines, is basically inversely proportional to the angles subtended by the source. So, in other words, we say if you have a large number of angles subtended by the source, as in the case of a LED is a very good example, then you may have very little spatial coherence. That means it's far away from being a plane wave. Or on the other side, if you have a very good collimated source, which can be the direction of which can be determined by a particular angle, just one particular angle, then we say it's a highly spatially coherent light wave. So, this is actually just talking about the randomness with which we are encountering this light, and these are essentially measures of that randomness. So, what's a natural step from here is to essentially treat this light waves as consisting of photons okay, and each of those photons may have a sub-wavelet and a particular direction and so on. So, you may actually be able to characterize these sources a little more easily when you go to the photon picture. But of course, that is founded by the fact that when you are talking about light emission or absorption of light, that tends to be quantized in nature. Okay. That is what Max Planck initially discovered, and then followed by Einstein, who said, okay, the propagation of light waves can be explained in terms of photons themselves, right. So, we are going to come to that, but before we do that, if we look at what we wanted to do initially is to, from the wave optics picture, we wanted to go to the electromagnetics picture, right. So, let us spend a little bit of time understanding that electromagnetic picture, and through that we will actually do one demonstration where you are quantifying the modes of an optical fiber, and through that quantification you are also going to understand how an optical fiber can essentially act like a spatial filter. Okay. So, that is what we are going to do in this lecture, is just capture a little bit of electromagnetic optics. Of course, that is actually a fairly large field. Once again, there are a lot of finer aspects to it, but we will just pick up some essential concepts from there before we move on to treating light as quantum or consisting of quantum object called photons. Okay. So, let me start here. The learning outcome for the next few lectures is actually identify the fundamental principles of photon optics and quantify photon properties. But before we do that, let us just look at electromagnetic properties of light. Okay. So, now we are treating light as electromagnetic waves, right. So, and of course, if we are treating light as electromagnetic waves, what does this have to satisfy? It has to satisfy the Maxwell's equation. So, you first of all have to satisfy the Maxwell's equation, which as you probably remember from one of your electromagnetics courses, consists of Coulomb's law, a divergence of the electric displacement current density is given by rho v. Your magnetic flux density is conservative, magnetic fields are conservative in nature. So, the divergence of magnetic flux density is 0. Then you have your famous Faraday's law, which says that you have a circulation of an electric field whenever there is a time varying magnetic field, and then you have Ampere's law, which was modified by Maxwell to include displacement current density, because originally Ampere was looking at only from a perspective of explaining the circulation of magnetic fields through a current carrying conductor, but of course Maxwell completed this picture saying that it could actually be through a displacement current as well, right. So, all of this constitute the Maxwell's equation with of course the constituent relationships, which say that your electric displacement current density is related to the electric field intensity in terms of through this constant, through this parameter called epsilon, which is permittivity, and similarly we said the magnetic flux density is related to the magnetic field intensity through mu, which is the permeability, right. So, in other words, permittivity and the permeability constitute the response of a given medium to an applied electric or magnetic field, right. So that's what it has to satisfy, and of course this is represented by the wave equation, right, and the wave equations are essentially for the electric and magnetic fields can be written in terms of, it is called the Helmholtz equation, del square E plus k square E equals to 0 and del square H plus k square H equals to 0, where k equals to omega root mu epsilon, we saw that before, represents the wave number for a given medium, right. So, what we understand from this now, of course, one of the things that we are starting to incorporate here is the fact that we are considering this electric and magnetic fields, okay, which was previously represented by a certain wave, we said the wave having a certain amplitude and phase, but now we are talking about electric and magnetic fields, and there is a specific notation that I have used, a vector notation, right, which essentially says, okay, there could be a specific orientation for this electric and magnetic fields, and if we look at that more carefully, let us say for the case of plane EM wave, let us say is propagating in positive z direction, which is essentially a solution of these wave equations, you will find that the electric field vector can be represented in terms of, if it is a plane wave propagating along a positive z direction, where are the field components? X and y, right. So, it can be expressed in terms of Ax Ex plus Ay Ey, and you could have a certain phase difference between the two components also in a generic case. So, you say e per j phi, and this is propagating in the positive z direction. So, it is going to accumulate phase as it is propagating. And once you express the electric field like this, then you have specific conditions where if phi equal to 0, that is Ex and Ey are in phase, what do you get? You have a certain polarization, certain orientation with which the electromagnetic wave is propagating. So, that corresponds to linear polarization, or if phi equals to plus or minus pi by 2 and Ex equal to Ey, then that electric field vector is going to propagate like this. It is going to go around, and the terminus of the electric field is going to draw a circle. So, that is what we call as circular polarization, and of course, we can go into very specifics and say if it is plus pi by 2, that corresponds to left circular polarization, minus pi by 2, that corresponds to right circular polarization, and any other case you probably have an elliptical polarization. So, the whole concept of polarization of light comes about when you go into the when you start treating these light waves as electromagnetic waves, okay. And there are certain manipulations you can do depending upon the response of your medium. If it is an isotropic response, then the polarization remains the same, but if you are going into a material which responds differently for different directions or responds differently for different electric field vectors, then you may start having certain polarization changes and some manipulations that we could possibly do. All of that will come back to it later on. Just enough to understand at this point that light actually could have polarization, could carry a certain polarization, right. This is all stuff that you would have seen in one of your courses in electromagnetic fields, right, basic courses in electromagnetic fields. Now, what we understand by solving this wave equation is that this key point that for a given structure you have certain field configurations that satisfy Maxwell's equation. So, everything as far as electromagnetic waves are concerned has to satisfy Maxwell's equations, and for a given structure it has to satisfy Maxwell's equations as well, and that is what is being represented by this wave equation. So, what we will find is for a given structure only specific field configurations are allowed, okay, are allowed by the Maxwell's equations. So, what do we call these specific field configurations? So, these are called the eigenmodes, okay, or simply modes of the structure, okay. So, you have this concept of eigenmodes or modes of a structure that come into the picture, because these electromagnetic fields will have to satisfy Maxwell's equations within that structure, okay. So, let us take an example, a very simple example of how this happens, what is the implication of this, okay, for a specific structure. So, let us take the example of total internal reflection, a waveguide. So, we already saw in ray optics, we took an example of an optical fiber, right, to say that the optical fiber can be used as a guide. Where did we use that guide in that case? We use that for endoscopy, right. So, we define basically a largish guide which can be designed to support endoscopy, right. So, let us take a similar example. Let us go back and revisit that example, and now we will revisit it from the perspective of modes of the waveguide, okay. So, let us say you have once again like we done before, you have a medium with refractive index N1, another medium with refractive index N2 such that N1 is greater than N2, you are going from a denser medium into a rarer medium, and we saw that if we come in with a light ray which is greater than a specific angle, right, theta greater than theta c defined as sine inverse of n2 over n1, right. So, if we come in with that, what happens? You have total internal reflection, and then we said, okay, if I put another parallel interface over here, and outside of that interface once again you have this medium n2, then you could support this bounce, right, and you can make a waveguide out of it, right. Now, of course, that is because if that is theta, this is also theta, right, and the reflected angle is also theta. So, that same condition is maintained as long as those two interfaces are parallel to each other, okay. So, we say that could act like a waveguide. Now, the question is, the key question is, this seems to suggest, does any angle theta greater than theta c, right, according to this picture, any angle greater than theta c should be guided, right, any ray with an angle such that theta is greater than theta c should be guided. So, is that true? Does any angle theta greater than theta c, does any angle theta greater than theta c survive in this waveguide? Okay. So, let's examine that a little bit, and to examine that, let's just go back and look at this propagation a little more closely, okay. So, clearly this wave vector over here can be decomposed into two constituent wave vectors, right, one pointing up and one pointing to the right side, right. And similarly, when we look at this wave vector, this will have a component that is pointing down, another component pointing to the right side, and similarly over here also you have the same case. So, after every bounce we see that there is one component pointing consistently along the direction of the waveguide, okay, and that component is called the travelling wave component, okay, because it's pointing to a wave that is travelling in that direction. But what about this other component? What about this component? Now, when we look at that component, we see that before the bounce it is pointing up, and after the bounce it is pointing down, right. So, essentially the fields, there are these two different fields that are interfering with each other in this region. So, we are defining a particular ray, right. So, what does that mean? That essentially means that we are having these wave fronts. If I were to draw these wave fronts, so we have these wave fronts like this, and these wave fronts after the bounce go like this, right. So, essentially we are saying this incident, the fields corresponding to the incident wave and the reflected wave are essentially interacting with each other, okay. So, when they interact with each other, what happens? depending upon their relative phase, they will have to have constructive or destructive interference. And the key point here is, for an electromagnetic wave to be supported in this structure, it has to satisfy Maxwell's equations. And Maxwell's equation says that I have to satisfy certain conditions at this boundary, but that same condition would have to be satisfied at this boundary as well, because the angle is the same, angle of incidence is the same, and then this material is, the interfaces are the same, right. So, whatever interference condition or whatever boundary condition that I am satisfying at this boundary is the same boundary condition that I will have to satisfy here, the same boundary condition that I will have to satisfy here every time it goes through the bounds. Okay. In other words, the electromagnetic field configurations that I am satisfying in this structure is symmetric about the center, and it has got to be consistent on either of these boundaries. One way of saying consistency is that if I am having constructive interference over here, I should have constructive interference over here as well. Okay. So, over the round trip, I should have constructive interference criteria. If I am looking at the incident wave and the reflected wave, the phase that I have accumulated between the two has to satisfy the constructive interference criteria. Okay. So, that can be simply written as, so what is the wave component corresponding to this? Let us say we said this is actually the z, let us say this is the z direction, the travelling direction, and x and y components are perpendicular to that. So, let us define this as x, and y is actually coming out of the screen, right. So, that would be y. Now, what we are saying is the phase accumulated for this vertical component over a round trip has to be integral multiples of 2 pi, so that it satisfies constructive interference criteria. So, I can write this as, if I say kx corresponds to the wave component in the vertical direction, and let us say this waveguide has got a dimension d. So, kx multiplied by 2d has to be integral multiples of 2 pi. So, that has to go through constructive interference criteria. So, the same pattern, essentially the same field configuration is consistent as this wave is going across. Now, if I were to write kx in terms of k, let us say k represents this direction of the wave vector, right, that's going. So, if this is k, what is kx? So, if this is theta, this angle, what is this angle? That is also theta. So, what is kx in terms of k? That will be k cos theta, right. And so, I can just write it as k cos theta multiplied by 2d is what you have on the left hand side. Okay. K sin theta would correspond to the other vector, the travelling wave vector, but this one that is pointing upwards will be this k cos theta, right. So, this can be written as 2 pi over lambda, and the it is not the free space lambda, it is not the free space wavelength. what is the wavelength of light in this medium? Lambda over n1. So, you have n1 here, 2d cos theta. So, this is equal to 2 pi m. So, this is equal to 2 pi m, right, and I can cancel this. So, I get this expression which says cos theta would have to be m times lambda divided by 2 times n1 times d, right. So, that has to be satisfied. So, there is a phase change at the boundary, that's a good point, somebody is just pointing out, but we are neglecting that for for effect, but yes, that is actually there is a component that basically says this is a phase change at the boundaries also that comes into the picture, right. So, we will have to take that into account also, but I am neglecting that just to drive home a particular point. So, I am not being completely rigorous about this, okay, but the key point is only certain angles theta m, right. So, only certain angles theta m which satisfy this condition will actually survive this waveguide. So, it will survive in the waveguide, everything else will have to be just radiated out, okay, or it will not even enter the waveguide, okay. So, that is what we are talking about. So, we are saying only specific angles are supported within this waveguide, and this is different from the picture that we had just looking at ray optics. If you say it just goes through total internal reflection, it can bounce, and there we say any angle theta greater than theta c should go through these bounces and it should survive. But what you will find is only certain angles are supported, and this is something that could be demonstrated. So, what we will do is we will send red light through this waveguide and we will show that the field configurations that are corresponding to only specific angles are existing within that waveguide, okay. So, that's actually a beautiful demonstration we will do today, okay. But come back and let's look at this a little more closely. So, what we are saying is theta m is different for different values of m, okay. So, when m equal to 1, right, that would have to correspond to the smallest value of cos theta m, right, because as m goes greater and greater, then you will have much more solutions that are possible, and cos theta m correspondingly will be lesser, right, because cos theta m goes to 1 when theta equals to 0, and cos theta m when it is pi by 2 that goes to 0, right. So, what we are saying here is theta m can take values. What are the boundaries for theta m? It has to be less than pi by 2 for sure, right. But what is the lowest value it can take? Theta c, right, because anything less than theta c is not even totally internally reflected. So, it will escape out. So, theta m is bounded within these values, and if we look specifically for m equal to 1, cos theta m has to be the lowest value, or in other words theta m is highest, right, and for it to satisfy this equation for larger values of theta m, for larger values of m, theta m will have to be smaller and smaller, okay, until it gets to theta c. So, and highest is pi by 2. So, what does that condition correspond to? Pi by 2. So, if this is my waveguide, pi by 2 corresponds to a condition where I am almost going straight down that waveguide, right. So, your fundamental, so your for m equal to 1, where we say you are going straight down the waveguide, that will correspond to what is called the fundamental mode of the waveguide, okay, and for, so that corresponds to m equal to 1, and for as you go to larger values of m, the theta m value gets smaller and smaller. So, that will correspond to bounces like this. So, this will happen for larger values of m, and the largest m that would be supported in this waveguide will just satisfy this condition of total internal reflection, okay, that is theta c, okay. So, do you understand? That is a fairly simple way of looking at modes in a waveguide, and specifically we are talking about modes in an optical fiber. In fact, the effect of this phi at the boundaries which we are neglecting, we can actually bring that back into this expression. We will actually post that out as a tutorial problem for you guys to look at in a little more detail. So, the number of modes supported, what do you think it depends on? It depends on this lambda over d value, right. So, you will find that if d approaches lambda, okay, only one value of theta m can be satisfied, and you will have only the fundamental mode propagating. So, you will find that as d approaches lambda, you will have only the fundamental mode. But if d is far greater than lambda, then that allows multiple values of m, right, and that would also allow multiple values of theta m to satisfy this expression, okay. So, when d is far greater than lambda, you have large number of modes, or in other words it is called a multi-mode waveguide, right. So, it is basically a multi-mode waveguide. So, as d approaches lambda, the size of the waveguide approaches the wavelength, you could have only one mode propagating in this waveguide, but as you open up the waveguide, you know, it's much larger compared to the wavelength, then you have a large number of modes that are propagated. And this picture, by the way, is not very different from what you might have encountered in electromagnetics in terms of rectangular, hollow, metallic waveguides, rectangular waveguides, cylindrical waveguides, they all have the same picture basically. But what we are considering here is an optical fiber which is a dielectric cylindrical waveguide, okay. But the principles are the same. since you have boundaries in the structure, you have this concept of reflection that comes into the picture, and whenever you have reflection, you have interference, and that interference actually gives the concept of modes of the waveguide, okay, right. Higher the order, more steeper the bounce, okay. So, for example, and this is something that we can probably demonstrate also, you send red light through a multimode waveguide and then you bend the waveguide, okay. If you bend the waveguide, what happens? You are essentially changing this total internal refraction condition at this point. So, when you bend the waveguide, some of those modes, the steepest modes that were guided in this waveguide may not satisfy the total internal reflection condition. So, they will escape out. So, you will see red light. Normally, when you have a straight waveguide, you will not see any red light coming out because everything is actually guided within the structure. But the moment you bend it, where I am talking about a multimode waveguide, you will have some of these modes escape the waveguide and you can see that corresponding radiation. Okay, so we will try to demonstrate that later on today. Okay, so let's move on. So let's try to get to a little more specifics, and so when we are considering an optical fiber, we are considering a core with refractive index N1 surrounded by a cladding with refractive index N2, okay. And if you analyze this optical fiber, what we want to understand is what are the modes that can propagate as a function of different frequencies. So, on one side I will write propagation constant, okay, that takes a value of 0 to 1, okay. So, 1 means it has got a very high probability that it will be supported by the waveguide, and 0 means it is very low probability that it is going to be supported by the waveguide. We will do that as a function of frequency, okay. If we look at this picture, and this frequency, we will, in the case of an optical fiber, we will look at it as normalized frequency, what we call as a V number, which is defined as 2 pi a over lambda. It has got a 1 over lambda dependence, and that is why it is called a frequency term, root of N1 square minus N2 square, okay. Have we seen this before, root of N1 square minus N2 square? That is the numerical aperture, very good, right. So, you are familiar with that. And 2a, a corresponds to the radius, so 2a corresponds to the diameter, which we have mentioned as d in the previous picture, okay, and of course this function of lambda. Now the propagation constant, which we will mention as b, is defined as n effective minus n2 divided by n1 minus n2, okay. So it is defined like this so that the analysis becomes a little easier, solving the wave equation becomes a little easier, okay. So that is why we are defining it in these two with these two parameters, but b going from 0 to 1 can be represented in terms of n effective. N effective, if b is 0, n effective would have to be N2, right, and if b is 1, n effective will have to be N1, okay. So what does this represent? This represents a condition where you have a waveguide like this with a core like this, but your wave is like this. So it is primarily propagating with a refractive index N2, whereas this condition corresponds to, if you have a waveguide like this, this condition corresponds to the fact that all your electromagnetic energy is well confined within this waveguide. So, you are going from very poor confinement, in which case all the energy is supported in the cladding, to a condition where everything is confined to the core. If you solve the Maxwell's equations, the wave equations, and we look at specifically what are the different modes that are supported, what you will find is something like this. You have a fundamental mode which is also called the LP01 mode, okay. And then at a specific value of 2.405, where does that come from? It comes from the fact that when you solve the wave equation and look at the field configurations will be expressed in terms of Bessel functions, and 2.405 corresponds to the first zero of the zeroth order Bessel function. So, you will find that the next mode comes about like this, and that is called the LP11 mode, and then at another value of 3.83 you will see a couple of other modes come into the picture. One is called LP21 mode and another is called LP02 mode. So, essentially what we are saying is, if I manage to stay within this region V number of less than 2.405, then I have only one mode that is propagated, okay. Or alternatively, if I have a condition where D, which is 2A in this case, 2A is much greater than lambda, then the value of V is very high, right. V could be 10 or maybe 100 also, and if you have that region, so you are looking at somewhere over here, and within that you are going to have all these modes, there are going to be hundreds of modes here. So, a very high value of V would correspond to a multimode fiber. And then you could of course have a fiber where for a given wavelength the V is defined somewhere over here, and you may be able to see in this case only these specific modes. The interesting part is these modes, which are generally called as LP MN modes, M corresponds to number of maxima in phi direction. What is phi here? Phi would corresponds to the azimuthal direction, okay, and N corresponds to number of maxima in R direction. R would corresponds to that radial vector, okay, that's pointing radially outside. So, LP01 for example will have a field configuration like this. It will be fairly dense at the center, and then it will fall off as you go outside in the radial direction. So, this will be LP01, whereas LP11 will look fairly dense in the center, but fall off, and then it will have two lobes. Essentially those, so why is it called LP11? Because when you are looking at the azimuth direction, you look at the half azimuth plane, okay. So, within that half azimuth, because one is a reflection of the other, within the half azimuth plane you will have one maxima, right, and radially outwards you have only one maxima, okay. So, that is why it is called a LP11 mode, and so you can imagine what a LP21 mode looks like. it is basically, it's got these 4 lobes like this. Once again, when we look at the half azimuth, you are going through 2 maxima. So, that is why you are calling it LP2, and then going radially outwards you have only 1 maxima, right. So, this is an LP21. So, what is a LPO2 mode? How is it going to look like? 0 means there is no variation in the azimuth direction. So, it is all uniform, but it has 2 maxima in the radial direction. So, how is that going to look like? You are going to have one central peak here surrounded by another ring over here, okay. So, that will correspond to LP02. And what we will find is, this is not just some vague theory, you will find that you can see all these modes. If you choose a fiber with whose V number is somewhere greater than 4, right. So, and what we see here is the V number is not like a defined quantity for one specific waveguide. Any specific waveguide, you have 2A and this NA defined, those are all material parameters and structure parameters. But wavelength, depending upon the wavelength at which you use it, the V number can change. In other words, let us say you have a 10 micron waveguide, you can come in with a wavelength of 10 micron and you will find that it acts like a single mode waveguide. You can come in with a wavelength of 1 micron and you will find that it has a different V value, it has got a higher V value. So, it will actually support more. So, you cannot generally call a fiber single mode or multi mode, okay. So, it is single mode at a particular wavelength, multi mode at a particular wavelength, okay. So, these are the concepts that we were going to see in the demonstration today. So, sorry I overshot my time, but let us stop here. Thank you.